Alright. So we're doing the substitution rule.
You can't multitask it.
And this is, it's called U-Substitution because we use the letter U. So it's a clever name for it. So we're going to find the integral of the derivative, it's f prime of g of x times g prime of x dx. What does that, if you just look at that for a second, what does this look like? The chain rule. Do you guys see it? So we took the derivative of the outside. The f prime is the outside of the function, but the inside of the function stayed like itself. And then we multiplied it by the derivative of the inside. So this is the chain rule. So U-substitution is what helps us integrate a derivative where that derivative was found using the chain rule. So it undoes the chain rule. Does that make sense? Mm-hmm. That's what we're doing? All right.
Oh. No!
So here's how you use U-substitution to integrate. You want to look for the part that is inside. You want to look for like the inside part of the function. Hey guys, we're doing notes and I'm videotaping it, so shh. So you look for the inside function and that's what you're going to call U. And then the du part is going to be the derivative right here. So if you can recognize what the inside of the function is, then you should be able to find its derivative somewhere in the problem because that's how the chain rule works. Okay? So du is going to be g prime of x dx. All right. So, and then just to remind ourselves so we don't forget, this reverses the chain rule. And so this is going to take care of a lot of the issues we were having as far as we were only able to integrate really easy problems. We weren't able to integrate more difficult ones because the chain rule, if you guys remember when we take derivatives, the chain rule shows up all the time. You guys remember that? Like it was often the case. So now we're going to be able to integrate more things. So when you do problems, they're still just going to tell you to integrate. You're going to have to recognize now when it's a simple problem and you can just go ahead and do it versus when it's a chain rule problem that you have to do. So this first one is going to be 2x times the square root of 1 plus x squared dx. So which part of that looks like it's the inside? Yeah, the 1 plus x squared is the thing that's inside something. So we're going to say that u for U-substitution is 1 plus x squared. So if that is the inside, what is the derivative of the inside? 2x, yeah. And do you guys see that in the problem? Do you see a 2x in the problem? Mm-hmm. Yes. Okay, so that means that we do have it. It does show up in the problem. Sometimes it could be, like when we did derivatives on occasion, sometimes you might have, maybe there was like a 2 that was part of the derivative, but it canceled out with a 1/2 that was already in the problem, right? Like we have things that simplify sometimes. So on occasion, we'll see a problem where we know the derivative is something, but we don't completely see it in the problem, and I'll help you guys work with those, because we'll see some of those examples today too. Okay, so that means that when we're integrating this, we're actually integrating the square root of u du. That's what we're actually going to integrate because I took out the 2x because that was part of the derivative for the chain rule. And I replaced everything underneath the square root sign with the u. So this is the U-substitution. Does that make sense? Check it all out. So I said the u part is just the stuff underneath. This part is the derivative. So if I'm going to integrate this, all I have to integrate is the outside function. I'm integrating the f prime of x part just to figure out what the integral of that is. So I'm going to rewrite this as the integral of u to the 1/2 because now I can use my little shortcut on it. So how do I integrate that? Add 1. So I've got u to the 3/2 divided by 3/2. And then there's a plus c on the end, right? And so what does that give me? 2/3 u to the 3/2 plus c, right? So at this point, we're done integrating it. So we took care of the difficult part of the integration by making it a more simple problem, using the u instead of using all the other stuff. And now I can go ahead and take the stuff that I used u to represent, and I can just plug it back in for u. So I'm going to say that this integral is 2/3 1 plus x squared to the 3/2 plus c. Nice little trick there. So we're saying that if you were to take this and get the derivative of it, remember how it works? You would take the derivative of the outside first, right? Because that's the chain rule, and leave the inside the same. And then you would multiply it by the derivative of the inside, right? So what we wanted to do is we know that we're not going to have an outside and an inside anymore like that, because we're undoing that chain rule process. And that's why we were able to get rid of that 2x, because we knew that was just part of the chain rule. We wanted to undo that. Okay. So here's the next one. We're going to do x to the 3rd cos of x to the 4th plus 2 dx. So can you guys tell what the inside is? Yeah, so u is going to be x to the 4th plus 2. And what is the derivative of x to the 4th plus 2? 4x to the 3rd, and we're going to have the dx in there. And this is almost represented in the problem, but what's missing? The 4 is missing. Does that make sense? So for us to say this problem, if it doesn't have a 4 in the problem, that means that we must have divided this stuff by 4 to get rid of it. Somehow there was a 1/4 in that problem that made that 4 go away. So when we do our U-substitution, we're going to put a 1/4 right in front of that integral, because we know that somehow a 1/4 canceled with that 4 and made it go away. Right? And I'm not going to use x to the 3rd because that's part of the chain rule, and I know that it's represented here in the derivative of u. So now I'm going to say that I'm doing the integral of cos u du. That's what I'm actually finding the integral of. And what is the integral of cos? Is it positive sign or negative sign? Positive. It's positive sign. So this would be 1/4 sine of u plus c. And then at this point, we can replace our u with the stuff that it represents again. So we can say that our final answer is going to be 1/4 sine of x to the 4th plus 2 plus c. Okay, so for this one, we're going to say the 3rd root of 2x plus 1 dx. I want you guys to go ahead and see if you can figure out what u should be, and if you can figure out what the derivative of u is. To see what should have been there. So I want you to figure out what the inside of the function is, and then see what the derivative should be. Well. What are we thinking for u?
2x plus 1.
Yeah, 2x plus 1. So what's the derivative of 2x plus 1? 2. So it's 2d, or dx, sorry. And then do we see a plain old 2 in the problem? No, there should have been a 2 in the front, is what we should have seen. So that means that somehow the 2 canceled out. How would that 2 have canceled out? There was a 1/2. So basically it just means we got to divide this by 2. So when we do our U-substitution to integrate, it means we're going to have a 1/2 in the front because we know that 1/2 would have canceled with the 2. So we're doing the integral of 1/2, and then it's a 3rd root of u du. I want you to go ahead and try to integrate that problem. So you're probably going to want to rewrite that radical. It's not very easy to work with right now. So here's how I started mine. I went ahead and added 1 to the exponent, so I got 4/3, and I divided by that 4/3. And how can I fix the problem to clean it up a little bit? Yeah, I've got the 1/2 on top, and this 4/3 is actually going to come up, and it's going to be a 3/4 because you flip it when you bring it up. So what's my coefficient for the u? 3/8. So I've got 3/8 u to the 4/3 plus c. And so what should my final answer be? 4/3 plus c. How do we feel about these?
They're okay, but when you get like the square root.
The 3/4, so we had, you add 1 to the exponent, right? And then you take that new exponent and you divide by that down here. And anytime we're dividing by a fraction, we can flip that fraction up. So that's what we were doing. Okay. So not our favorite thing, but not the worst thing we've ever done.
Yeah.
It's not a terrible place to be. Okay, we're going to look at how to evaluate some of these. So now we have a definite integral. Do you guys remember what these ones are called if there's no numbers? Indefinite. Yeah. Indefinite. That's where you have the plus c on the end. We don't know exactly what it is. Here we have a definite integral. We're evaluating from 1 to 2. And it's 1 over 3 minus 5x squared dx. So on this one, what should we do? U is 3 minus 5x. So what's the derivative of u? -5 dx. Do you see that derivative in the problem currently? So I'm going to go ahead and divide it by -5. So I know that when I do this integration, I'm going to have a -1/5 in the front. And then what should we get when we put the u in there?
1 over u.
Yeah, 1 over u to the second. And how should I really think of that?
What's in the negative? I mean, u to the negative.
Yeah, so -1/5, and this is u to the -2. Okay. Now you'll notice when I wrote down the integration, I did not keep the 1 and the 2 there. Does anyone know why I didn't keep the 1 and the 2?
Wait, what?
No, we don't know.
Is plugging a 1 in for x and a 2 in for x the same as plugging a 1 and a 2 in for u? No, because does u equal just x? Is that what u equals? No, what does u equal? 3 minus 5x. Okay. So yeah, don't put a 1 and a 2 there because then you'll think, oh, I can plug in 1 and 2, and you cannot. Okay, you cannot. You can only plug it in. You can only plug the 1 in and the 2 in if your answer is in terms of x. Does that make sense? Okay. So we are going to do it first, where we actually use the 1 and the 2 to get the final answer, and then I'll go back and I'll show you how to do it if you want to plug a number in for u instead of plugging a number in for x. Okay. But if we're going to plug the numbers in for x to evaluate the integral, we are not allowed to put numbers here because it should be different numbers for u, since u and x do not represent the same thing. Does that make sense? Okay. So let's go ahead and finish this problem. How do we get the integral for this? Plus 1 would be -1, right? Divided by -1, and we have a -1/5 in the front. So what is that when I simplify all of that? So yeah, 1 over 5u. Okay. So if we fix it, that's what it is. So now we can go back and we can plug this stuff in for u. So that should be 1 over 5 to, and then it's multiplied by 3 minus 5x. And now if we want to evaluate it from 1 to 2, we can. Because I've written it so that I'm plugging the 1 and the 2 in for an x, which is how the original problem was written. All right, so go ahead and figure out what that should be. We're going to plug the 2 in first and see what we get for 2. Also, did any of you guys accidentally steal my calculators? Because I'm missing 2. Just bring it back. I won't even notice, except I'll be happy that it's back. Martin, you're missing yours too. Did you get yours yesterday? Yeah. I left it on my desk.
You got it?
Okay, so what'd you guys get when you plugged in 2? -1/35. Perfect. And then if we plug in 1, what'd you guys get when you plug in 1? -1/10. So if we add those together, what do we get? Oh, no, we're subtracting. You're right. You subtract. Minus those. 1/14. Okay.
Cool.
All right, so here is the other way to do it. We're just going to write on the same problem. I'll do it in purple so you guys can see what I'm doing. So if I want to go back and just evaluate the u part of it so that I don't have to do this part where I plug stuff back in, then I can take 1 and plug it in for x here to see what the u would be when x is 1. So I would say u is 3 minus 5 times 1. So what would that u value be? -2. And then u is 3 minus 5 times 2. -7. So that means that if I was going to evaluate with the u's, I would go from -7 to -2. And that would mean that right here I could evaluate it from -7 to -2. Oh, I did those backwards. Did I do those backwards? Smaller to bigger. No, except the one I plugged in. Yeah, no, the numbers end up being backwards actually. So I plugged in the -1 to get the -2. I plugged in the 2 to get the -7. And then you always they're going to be backwards, but think about it because it has to match up with the other one that we did. So you plug this one in first and subtract it from that one.
I'm confused.
Yeah. Okay, so if you look at this, the 1 was on the bottom, right? You guys see that? We're gonna walk through it again.
Yeah.
Because remember, if you flip your numbers, we usually say the smaller number to the bigger number, but if you flip your numbers, all that happens is it makes your answer negative. It will change the sign of the answer. So you have to be consistent. The 1 was on the bottom, and when I plugged in 1, I got -2. I put that on the bottom.
Okay.
The number on the top was the 2, and I plugged that in. I got the 7. So yeah, so typically when we do these, we plug the top one in first, and then we plug in the bottom one, and we subtract those from each other. So when we plug the top one in, that's where we get the 1 over negative 35, right, which matches up with this fraction. And then we get subtract, and when we plug in the bottom one, we get 1 over negative 10. Right? So even though the numbers aren't in the order we expected, we still got the same answer. Okay? So 2 different ways you can do it. It's up to you. You guys can, if you want, you can replace the u with those numbers so that you can evaluate the u version, or you can just wait till the very end and plug the original numbers into the version that still had x's. I did the x version because that made more sense to me. So that's how my answer keys work. Okay. Do we see where that comes from, though, how the u comes into play? So just make sure that you don't plug the 1 and the 2 in for u's because they were defined by the x's originally. Okay, so they should be plugged in for an x. All right, here's the next one. We're going to do one similar to that with trig functions because I know you guys love trig functions.
Is that sarcasm?
That was sarcasm. Yep.
Cool.
It makes my heart sad, though, because I really love trig. And I'm just sad every day that you guys don't love it, too.
See, your love is our hate.
That hurts. That hurts, James. That's deep. All right, so what should the u be? 2x. And then what should the derivative of that be? 2 dx. And do you see that derivative in the problem? No. So what should we do? Yeah, so we're going to put a little 1/2 in front of our integral. I am not putting the numbers for my integral because I'm about to switch to u's, and my numbers had to do with x's. So I'm going to integrate what? Well, I'm integrating sine, but my answer is going to be sine u du. Okay, so if I integrate that, is it going to be negative? Yes, you're right. It's going to be negative. So, like Sam said, the antiderivative of sine is negative cos. Good job. I am not going to put a plus c on the end because this is a definite integral. I'm going to evaluate it. Do you guys want to evaluate it with the u in there, or do you want to evaluate it when we plug the x back in? Plug x back in? Okay. So I'm going to say this is negative 1/2 cos. If I plug my x back in, that would be 2x. And I'm evaluating it from pi fourths to 0. So we got negative 1/2. 2 times pi fourths is... Ooh. 2 pi fourths, which is pi halves. Good. Minus 1/2 cos 2 times 0. 0. Okay. So I'm going to picture the unit circle because we can do this without a calculator. What is the point that's right up here on the unit circle?
1.
Yeah, 0, 1. Good. What's the point right here on the unit circle? 1, 0. Okay. So negative, I've got negative 1/2 times, which value is the cos value? The x. So times 0 minus 1/2 times, oh, that should have been a negative 1/2. So minus negative 1/2 times cos of 0 is 1. And so what does that end up equaling?
0 negative.
So this is 0, and minus minus,
What equals 1?
it equals 1/2. Good. Look at us doing all that work without a calculator. I mean, you guys were kind of telling me things, maybe, hopefully, a little bit, kind of.
And I'm over here typing numbers.
Most calculus teachers would say that calculus is not really about calculus. It's just a lot of really intense algebra. Have you guys noticed that? Just a lot of algebra all the time. When students make a mistake, it's usually not a calculus mistake. It's usually an algebra mistake. All right.
I'm about to go back and review all this trig
Is this a definite integral or an indefinite integral? Indefinite. So are you going to be plugging numbers in? No. What are you going to have on the end? Plus c. Okay. Go ahead and see if you can recognize what your inside function is. And then after you find your inside function, I want you to find the derivative of it to see what that should be. Was a great question. So, what's our u? X plus 7. And I'm going to think of that as x to the 1/2 plus 7. That makes my life a little easier. And so what's the derivative of this? So, okay. And in this problem, they didn't have rational exponents, they had radicals. So how would this have shown up in our problem? What would it have looked like? Square root x, right? So what part of it do you see in the problem? I see the root x on the bottom, right? What do you not see in the problem? The 2. The 1/2 is not there. The 2 is not on the bottom. So what would have happened to get rid of that? Multiply by 2. So that means that when we do this integration, we're going to have a 2 that's being multiplied in the front. How did we feel about getting there? Did that make sense?
That was fun. With the walkthrough street.
All right, so what do we have now?
Now you gotta find
So we're ignoring this because this is part of the derivative, and this is where we put our u. So what are we integrating? U to the 8th. That's what we're integrating.
Why wouldn't it be u to the 8th over? Oh no, because square root x was in there.
Square root x was part of your derivative. That's why you're ditching it. Yeah. Okay. So the u to the 8 is this part. The 1 over root x and the dx is part of that du that we had. So it's all taken care of. It's just kind of simplified. So when we take the integral of that, when we find the antiderivative of that, what do we get?
2 integral 9 over.
Yeah, so it's u to the 9th over
Good job, Patrick.
9. So what would that be?
Got something against this.
2/9 u to the 9th. Okay. And then, what do we have on the end? Let's see. And then, what do we do now? So we've got 2/9, and then we got root x plus 7 to the 9th plus c.
Where Ricky is? Gotta hear that.
How are you guys handling life at 3:06 on Thursday? You're not feeling it?
I'm on 218.
All right. You guys look you look a little comfortable, so I'm going to give you another trig one.
Miss Brooke.
I'll raise you to 1,000.
Yeah, 3.
I'll raise you to 1,000.
I'll let you do that.
It's gonna take forever.
Coach, do you want to raise it?
It's not going down. But what if that's right and ready to do like that? What if
You got to bed early last night and sleep good tonight?
Sign of sin X.
If
I
you
never
see
gonna think
Oh, Miss Right, why?
I know this one looks a lot crazier, right?
Yep.
But where does it look like it has an inside? Yeah, that stuff inside, right? So that's the inside. You're exactly right. It's going to be sin x.
Oh, no, it's back to think of this.
Hold on. This is sine of sine x.
Yep, it's sine with sin x inside.
How did that even make sense?
Oh.
It
It does.
We did some problems like that.
Mad that it's there.
Yeah.
Now, what about the coast?
This one, it looks worse than it is. It looks really confusing, but it's actually not terrible. So sine x is inside. What's the derivative of sine x? Wait, it's just regular cos. The derivative of sine is regular cos. Do you see the derivative in the problem? Yes. Do you see the entire derivative in the problem? Yeah, the entire derivative is there. It's right here on the end.
Oh.
Yeah.
So,
All right. So at this point, when we integrate this, what are we going to integrate? Because this is the inside, right?
Sine
And this is the derivative.
sine of u.
Sine of u is what we're integrating.
God, James, you're so smart.
Caitlin got it.
Good job, kid.
And what's the integral of sine?
I have it in my notes.
It's negative cosine. So this is negative cos u plus c. And then what do we do?
Negative cosine.
Negative cosine.
We replace the u with what u equals. So it'd be negative cos of sine plus c.
That's it. Everybody eats.
Now, if you want to check your answer, just do the chain rule. So if we think about this, if we were doing the chain rule, we would say, what's the derivative of negative cos? Positive sine, and we keep the inside the same. And then we would multiply that by the derivative of the inside. And what's the derivative of the inside? Cos. And so that's what we have. So if you need to check your answer for these, it's not a terrible process on some of them. You just have to, just go back to your problem, do the chain rule on it. You should be able to see. Okay. All right. We got All right. We got one more trig one, just because I want to make sure we can handle. All right. Oh, sorry. Boop. Indefinite.
Oh my God. Another example.
So many examples.
Oh my God.
I know. Well, because usually I do some in the video and then some in class. We're just doing all of it right now.
Great.
All right. So what's the inside?
Oh my God, Miss Russell, you said there was no notes tonight. I would have
There's no notes tonight.
Then what's homework?
Just practice. Just practice. All right. So cos x plus 2. What's the derivative of that? Negative sine x dx. Okay. Yeah, and we almost see that in the problem, right? We see the sine x in the problem. What do we not see? We don't see the negative, so we know that this whole thing, somehow they got rid of the negative, which means we need to have a negative in front of our integral when we do the U-substitution. Okay, so this sine x is part of the derivative. This is the inside.
Yeah, mine's an S.
And so what are we finding the integral of? Cos u. And what is the integral of cos u? Yeah, and it's not negative sign. There's a negative in front of the integral, and that's what is making our answer negative. So negative cos, the derivative or the antiderivative of cos is just sine. So that would be sine u plus c. And what are we going to replace the u with?
Cos x plus 2.
Cos x plus 2.
Okay. Everybody eats.
Now let's chain rule that.
All right.
Your mind?
Hey, Pat, bro.
Okay, so there's two little things that I have to show you. And these are potential shortcuts for problems. This is not something you necessarily practice a bunch. This is just something that you keep in your back pocket and then might recognize it, and it will save you some time. So this is integrals of symmetric functions. So think like if I was taking, if I wanted the area underneath a parabola, because that's symmetric, depending on where it's centered. Does that make sense? So this is just shortcut the process a little bit, save yourself some trouble. So, and this works if f is continuous from negative a to a. So we're saying that when we're finding the area underneath the curve, we're doing the same amount to the left of the x-axis as we are to the right of the x-axis. So it might be like find the area underneath the parabola y equals x squared from negative 5 to 5 or something. Okay. Shortcuts. So if f is an even function, you guys remember learning about even? I don't mean to write off. If f is an even function, anyone remember how to tell if it's even? If you can plug in a negative x, and when you plug in a negative x, you just get back to the original function. So like x squared, if I had the function y equals x squared, and I plugged in a negative x,
So pretty much
that would be,
that's on the literally an even exponent.
yeah, if it's all even exponents, definitely, but there's some other ones. Yeah. So if I plug in a negative x, what happens when you do negative x squared? You get the same thing. So that's an even function. They're also symmetric over the y-axis, and that's probably how you're going to check these, to be honest.
Okay.
Yeah. So if you can fold it across the y-axis, fold it in half across the y-axis, then you can do this. So I think this is pretty much common sense. My guess is that you guys could make a guess as to what this is. But if I wanted to know the area under a curve, let's say that I was talking about the curve x squared, and I wanted to go from negative 5 to 5, I'm going to rewrite this, and I'm going to say that's actually the same as if I just go from 0 to a of that function and multiply it by 2. Because it's symmetric, right? Yeah. So that if I just find the area that's to the right of the x-axis and multiply it by 2, that's going to show me the area of both sides. Okay. So like here's a picture of that. If I've got my parabola right here, and this is my negative a value, and that's my positive a value, then I can just add. I could find both of them and add them together, or I could just multiply it by 2. Find one side and multiply it by 2. The other one is if we have an odd function. And odd functions are a little bit different. If you plug in a negative x, you actually get the negative version of the equation. And the classic example of this would be x equals y to the third, because if you plug in a negative x for this one, it'd be negative x cubed, right? The negatives would not cancel out if you did that. And these are not symmetric to the x-axis. It's not just opposite. Does anyone know how odd functions are symmetric?
Like if that, I guess,
No, you're thinking inverses are y equals x. They're symmetric to the origin. It's if you spun them. If you put a pin in the origin and then spun it around, that's how it's symmetric. So they're symmetric to the origin. So this one is saying, and I'm going to draw a picture first, and you guys can probably figure this out. So here's the cubic function. Let's say that this is negative a, and this is positive a. So it would be 0, yeah. So if it's an odd function, because the area on either side is going to be, oh, my drawing was bad. Don't copy my drawing. It's supposed to be between the curve and the x-axis. That was my bad.
But if it's
It should be right here.
oh,
I shaded the wrong part. So yeah, so the areas are the same shape. There's just one of them is on the underside of the x-axis, which means it's a negative area. The other one is on the positive side, and so it's a positive area, and since they're exactly the same shape, they cancel each other out and equal 0. So if you are looking at something, and your clue when you're doing these problems is going to be that when you evaluate it, you have the same number, just the positive version of the number and the negative version of the number. And if that happens, then you'd want to check and see if that function is even or odd. And if it is, you don't have to do any work when you evaluate it. You just say, oh, just double the area, or the area is 0 automatically. And I will tell you that this happens one time on the homework assignment. There's one problem you don't have to do, and you'd get stuck. You couldn't do it if you didn't know this rule. So that's why you're doing it now. We'll see if you notice which one it is. Does that make sense for you guys, looking at that? I think those are fairly intuitive, but easy to maybe forget about. So, all right.
It's so long.
Whew.